You guys get to hear me narrate through my step process. All right. Good morning. I think we are all good to go. Okay, so today we are going to pick up with lecture set number 2. I'm just going to put a little date here so we know the starting point. I almost wrote 2001. All right, so last class, we finished lecture set number 1. So lecture set number 1 essentially is a definition-based lecture set. It's certainly one of the shorter lecture sets that we're going to see in the course. And for the most part, what we did is just cover basic definitions like what is data, what is a variable, what are the types of variables, what are the different types of statistics, what are the different types of, studies that you can observe data from. In that case, we talked about the observational study versus the designed experiment. And following that, we moved into lecture set number 2, which is what we are going to continue with today. We finished discussing 2 plots. So the pie chart and the bar chart, which are shown here on slide number 9. And our pie chart and our bar chart are graphical displays for qualitative data. So the first part of lecture set 2 was devoted to organizing and visualizing qualitative data. And as a reminder, a qualitative data set is one in which the variable of interest is non-numeric. So a label or a classification of some kind. In this particular instance, our data set has one variable, which is the era in which these classical painters went to school. And essentially what we are doing is we are organizing and visualizing this variable using the observations, the 50 observations that we have in front of us. Okay. Now to do this, we created what is called a frequency or a relative frequency distribution. The frequency distribution is essentially just a list that gives you the number of times each of the different outcomes occurred. The relative frequency is a similar idea. The relative frequency is a similar idea, except it gives you the proportion of times each of the different outcomes occurred. Okay, so one of the questions that just came up in the chat is, what is ordinal versus non-ordinal qualitative data? Ordinal data is one that would have an inherent order to it. So an ordinal qualitative data set would be one where the categories also fall in line relative to one another. So you might think of this data set as being ordinal qualitative because technically each of these eras occurred one after the other. I don't know off the top of my head which era would have come first. Let's say for illustrative purposes that the Renaissance era came first and then the Mannerist era and then the Cinquecento. Then we would have an inherent order in the frequency distribution representing which of the eras came first. Non-ordinal data would be data where you do not have a ordering of the observation. So for example, if you considered gender of a set of people, it wouldn't matter which gender you listed first or second or third, etc., because there is no inherent order for the genders. Does that make sense? Okay. So today we're gonna continue with discussing ways of organizing and visualizing data, but we are gonna change. Sorry, I'm just trying to find if there's a good. We're going to change our focus from qualitative to quantitative data. Now, for the most part, the beginning or the starting point for organizing quantitative data is the same as the starting point for organizing qualitative data. That is, for quantitative data, we would still be interested in constructing a frequency and a relative frequency distribution. The difference is the way in which we compute the frequency and relative frequency distribution depends on the grouping method that we utilize to organize that data into different classes. So with qualitative data, we have a natural grouping because we can organize the data based off of the label that is associated with it. For example, we put all of the Mannerists together, we put all of the Cinquecento together, we put all of the 16th century painters together. With quantitative data, you don't always have that same natural ordering. It depends on the type of quantitative data that you are working with. As you will see, when we have discrete quantitative data, the process of organizing that is almost, I would say, exactly the same as for qualitative data, because discrete quantitative data tends to provide a natural grouping because you can just put all of the similar numbers into the same category. But as we transition to continuous quantitative data, we no longer have that same ability, and we have to construct what are called bins, which are essentially ranges in which the different data points can fall. So we're going to look at an example of each of these, and then following the illustration of these binning approaches, we will talk about visualizations. Okay, so the first type of grouping method is single value grouping. Single value grouping is going to be the most similar to the grouping method we used for qualitative data. So we use single value grouping when we have discrete quantitative data, we have a low number of unique values, and we have a high number of repetition, okay? So for example, the data set shown on slide 13 gives the number of gears in 32 randomly selected cars. Okay, so here, number of gears is the variable. Okay, and we can see that this variable is discrete quantitative. Furthermore, when we observe the data, we can see that we only have 3 unique values, 3, 4, 5. Okay, so there's only 3 different numbers in the data set. However, for each number, we have a high amount of repetition. So we have a lot of 3s, a lot of 4s, and a fair number of 5s. So this is the kind of data set where we would want to utilize single value grouping, okay? Discrete quantitative data, low number of unique values, high amount of repetition. Now you can see that in discrete value or in single value grouping, the process of creating the frequency and relative frequency distribution is identical to the process we utilize for qualitative data. First, we establish our groups. Okay, so the groups or bins are the unique. Okay, so the groups or bins are the unique numbers in the data set. And then we simply count how many of those values do we have. So we have 15 3s, we have 12 4s, and we have 5 5s. And then we compute the relative frequencies in the same way we did before. For example, here we would have 15 over 32. Here we would have 12 over 32. And here we would have 5 over 32. Okay. Any questions? So the next type of binning method is called limit grouping. Limit grouping is also utilized when we have discrete quantitative data. However, in this case, we would have a high number of unique values and a low number of repetition. All right, so for discrete quantitative data, we have two binning approaches: single value grouping and limit grouping. Single value grouping is utilized when you have a lot of repetition and a low number of unique values. Limit grouping would be utilized in the opposite case, when you have low amounts of repetition, but a high number of unique values. Single or limit grouping is our first illustration of what we would think of as kind of a true binning method. So we have to artificially create different groupings that the observations can fall within. Now, there isn't a right or a wrong way to do this necessarily. You can create as many bins as you want or as few bins as you want. But ideally, the number of bins selected would be such that you can visualize what we call the distribution of the data set. And this is a point that we will come back to in a little bit after we talk about the last grouping point, or the last grouping method. Okay, so here's an example of when we might use limit grouping. You can see here in this data set, we have the waiting times between eruptions of Old Faithful Geyser. Okay, so these waiting times this is the variable of interest. All right, and you can see that this is presenting itself as discrete quantitative data. Now, we've already talked about how with time, the definition of the type of quantitative data is somewhat variable. Like when you're talking about a measurement that can be measured very precisely, like time can, it could be continuous or it could be discrete. The data presents itself as discrete in this case. Therefore, limit grouping would be the most appropriate binning procedure. Now you can see that in studying the data set, what we have here is a situation where there's a lot of different numbers. Okay, the amount of repetition is very low. You can see 78 repeats itself a few times, four times or so. 76 repeats itself a couple of times. 81 repeats itself a couple of times. But we have a far greater number of unique values than we do repeated quantities. Therefore, we need to construct our own bins in order to place the objects into the bin. So an example of the bins is given here. Okay, so you can see that the bins are simply ranges that cover all of the different values in the data set. In this situation, I have selected to use bins of size 5. So for example, here, my lower limit is 45. My upper limit is 49. And therefore, the bin length is going to be 5, which seems a bit strange because you're thinking 49 minus 45 is 4. But you can place objects into the bin that sit on the limit. So we have 45, 46, 47, 48, 49 as possible values to fall within the bin. So there's 5 different numbers that can sit within that first bin. You'll notice that as the bins progress, we always use bins of the exact same size, and the bins cannot overlap. So this is very important. We cannot have a situation where an observation can fall into more than one bin. The bins have to cover unique values. So we have 45 to 49, and then we move to 50 to 54, then we move 55 to 59, then we move 60 to 64, 65 to 69, 70 to 74, 75 to 79, etc. Now, once we have the bins established, the last part is simply taking the data point and dropping it into its bin. So we start with 78. 78 falls within 75 and 79. So it gets dropped into this bin here. Okay. And then we have 87 as the second number. 87 falls between 85 and 89. So we drop it into that bin there. Okay, and then we proceed in the same fashion until all of the data points have been placed into a bin. Once we have our data points in a bin, our frequency and relative frequencies are computed in the exact same way that they were before. Any questions? Yeah, lots of different numbers, low amount of repetition is when you would use limit grouping. Okay, the last grouping method that we're going to talk about is cut-point grouping. Cut-point grouping is what we use when we have continuous quantitative data. So we have two approaches for discrete quantitative data that depends on how many different numbers you have and how much repetition you have. We only have one grouping method for continuous quantitative data. And this approach works in the exact same way that the limit grouping works, except that our groups are now going to include decimal places of accuracy to reflect the fact that we are measuring objects more precisely. So an example of cut point grouping is given on slide 17. You can see here that we have a data set giving the duration of 22 eruptions of Old Faithful geyser. So this is the duration of eruptions. So this is the variable. Okay, and you can see from the display below that this is continuous quantitative. All right, so the way that cut point grouping works is we first identify that we're working with continuous quantitative data, which essentially means that we're working with data that have some decimal place amount of accuracy associated with it. And then we construct bins to drop the data points into. You can see here that the bin construction is very similar to what it was with limit grouping. The only difference is because we are working to some number of decimal places of accuracy, we now write the limits of the bins as being, in this case, for example, under 2. So what this means is that we would have 1.5 to like 1.99999 repeating. Okay. Sorry, I think I need round brackets there. I always forget round versus square. I need to check that real quick. I think I need a, oh yeah, endpoint is included. Okay, so we're good there. Yeah. Yeah, good. Thank you. Right. So yeah, it's one of those things. Right. So, but the point here is we write under 2 as a, you know, it's kind of like the 1.99s can repeat forever, hence why the bar is sitting there. Like this would be like 9 going on forever. So 1.99999 all the way up to under 2 would be the same thing. Like here, for example, we would have 2 to 2.499, repeating forever. So these under 2 or this decimal place notation, this means the exact same thing. So you can use them interchangeably, but just to clarify what I mean by under the number means like right up until as close as you possibly can get to that value. Because again, when we construct the bins, we don't want there to be any observation that can fall into multiple bins. They have to be placed uniquely across the bins. Once we have our bins established, all we have to do is drop the value into the bin, right? So same idea as before. Let's say we start with 3.85. 3.85 is going to be between 3.5 and just under 4. Then let's say we do 4.42. 4.42 is going to be from 4 to just under 4.5. Okay. And then once we have all of our objects binned, we count the number in each bin, same process as before, and then we compute the relative frequencies, which would be done in the same way as before. For example, here we would have 1 over 22. All right. Any questions? Technically, so sorry, the question is single value grouping the only sorting for qualitative data? Sorry, I forgot. I'm going to read the questions out for the people that are watching the recordings, as much as I can remember to. Okay, so is single value grouping the only sorting for qualitative data? The answer to that question would technically be no, because single value grouping is for discrete quantitative data. However, the process of single value grouping is the same for qualitative. So in that sense, yes, it is the only one. What? It's okay, the little circles 1 and 2 are just the observation that I'm binning. So observation 1 is 3.85, that falls in 3.5 to under 4. Observation 2 is 4.42, so that follows from 4 to under 4.5. Did that make sense, Adina? Okay, cool. And then Brooke, where would 3.5 go under 3.5? So the bottom, okay, so the bottom number is inclusive. So the square bracket here means include. So 3.5 would get dropped into the same bin as observation 1. So the bin with 3.5 as the lower limit. Does that make sense, Brooke? Okay. Michael, with cut point grouping, is it standard to always use under, or is it up to you to choose how it's grouped? That's a good question. Conceptually, I think you don't have to do it this way. Like you could go, I guess you could do something like 1.5 0.0000000001 and like above 1.5 to exactly 2 would work in the same way. This one is just a little bit easier to understand, I think, because you're going up to a cut rather than starting at a cut. Does that answer your question? Raleigh, what is the class midpoint? The midpoint would be like the middle object in the class. It's a little bit easier to see class midpoints with the limit grouping. So for example, with the limit grouping, we would have like 4.5, 4.6, we would have 45, 46, 47, 48, 49. So 47 would be the midpoint of the class. With the cut point grouping, it's a little bit more difficult because technically you're not fixed at an upper limit, but in this case, the midpoint would essentially be the average of the two values. So something like 1.5. I guess what we could just do here to make it simple is just say the midpoint would be the average of 2 and 1.5, so 1.75, but it's not exactly at 1.75. Does that make sense? Essentially, yeah. Any other questions before we move on? So this is the last grouping method, and then we're going to talk about visualizations next. Oh, if it were an equation, would we say approximately? Yeah, that would work. Approximately equal to the average of the upper and lower over 2. Any other questions? It's good. Lots of questions at 8 a.m. I like it. Let's keep it up. Any other question? I guess I shouldn't push my luck. Should I just move on? Okay, I'm going to slowly move on. All right, so for organizing quantitative data, we talked about 3 different approaches. On slide 18, those approaches are summarized. So we have the single value grouping, limit grouping, and cut point. Single value and limit grouping are both for discrete data. The single value is when we have a low number of unique values, but high amounts of repetition. Limit grouping is also for discrete data, but in the opposite situation. So a lot of different values, but low amounts of repetition. Cut point is what we use for the continuous data, continuous quantitative data. All right. So the next thing we're going to talk about is visualization for quantitative data. There's actually 2 different graphics that we're going to utilize to visualize quantitative data. The first one is what is called a histogram. The histogram is essentially the quantitative box or the quantitative bar chart. Okay, so for qualitative data, we talked about pie chart and bar chart. Sorry, pie chart and bar chart. For quantitative data, we're going to use a histogram, which is essentially the same thing as a bar chart, except that the numbers or the bars are now going to connect with each other to represent data flow from one bin to the other. The other approach that we're going to talk about is a box plot. The box plot we will come back to later in the lecture set, right near the end of it actually, because before we can talk about box plot construction, we have to define what are called percentiles and 3 specific percentiles, which are the first, second, and third quartiles of the data set. So starting with the histogram is our first visualization for quantitative data. And like a bar chart, a histogram can have different quantities on its y-axis. It can be a frequency histogram, it could be a relative frequency histogram, or it could be a percent histogram. Visually, all of these things are going to be the same, assuming they use the same bins. The only difference is how we are writing the value on the axis. So we can write it as counts, we can write it as decimal places, or we can write it as percents, where the percent is actually just the relative frequency multiplied by 100. So really they're very similar. Like a bar chart, a histogram has 2 axes. So we have a y-axis, which represents either the frequency, the relative frequency, or the percent. And we have an x-axis, which is going to be marked based off of the bins that we are working with. Okay. All right, so constructing a histogram is done in essentially the exact same way as constructing a bar chart, except that on the x-axis, we don't have labels anymore. We now have numerical values. So for example, let's return to our data set that we utilized in the Cutpoint grouping method. Okay, so here we have again the duration in minutes of 22 eruptions. Okay, so this is our continuous quantitative data set. Right, so this is the same data set from the Cutpoint grouping example. So if we go back, if we go back to slide slide 17, we're going to be using these same bins from slide 17 to construct the histogram on slide number 21. So you can see that the way the histogram is constructed is we start by choosing the type of histogram that we're working with. So in this case, we're working with a frequency histogram. All right. And then what we do is we construct bars whose length matches that of the bins that we had before. So for example, here, this would be the bin that corresponds to 1.5 to under 2. Okay. And then this would be the bin that runs from 2 to under 2.5. And then we have these two middle bins here that don't have any values. That's because no objects fell into the class. But technically here would be the next bin. So this would be 2.5 to under 3. And then we continue to progress until all of our bins have been accounted for. And then what we do is we simply draw the bar to the height of whatever variable we are interested in. So for example, we're using a frequency histogram. So the first bar gets drawn to a height of 1 because we have only one observation between 1.5 and under 2. The second bar gets drawn to a height of 5 because we have 5 observations between 2 and under 2.5. And then we have 0 in the next class, 0 in the next class. Then we have 5 observations between 3.5 under 4, 5 observations between 4 under 4.5, etc. Okay. And again, oh, thank you. Yeah. Typo. Right, so this, again, this would be our example of a histogram. As I mentioned before, we can have different types of histograms, but really they're gonna look the exact same regardless of the y-axis. So for example, let's suppose that we wanted to turn this into a relative frequency histogram. So let's say that instead of having the frequency axis there, we change it to relative frequency. All right. All that would happen in this case is that instead of having counts, we would now just have the relative frequencies. So this would become a 0. And then we would just need to compute the relative frequencies corresponding to those same frequencies we had before. I'm just gonna compute those real quick here. And so then we would have 0.045 repeating. Here, I'll just move this over so it's a little more legible. Okay, and then we would have 0.09 repeating. And then we would have 0.136 roughly. And then we would have 0.18 repeating. And then we would have 0.227. Okay. See, the point is that regardless of what we write on the y-axis, given that the bins don't change, we're going to have the exact same display. We're just changing the information on the y-axis, so we're visualizing the data in a slightly different way. So instead of looking at it as just raw counts, we can look at it in terms of relative frequency or in terms of percentage. And the percentage would be exactly the same as the relative frequency, except we're just multiplying each of the relative frequencies by 100 to convert them into percents. Any questions? So the bars represent the number of observations within each bin. Yeah, 3 of them do right here. 5, 5, and 5. Oh, okay. Right, so the bars represent the height, or the bars represent the number of observations in the bins. So if we go back to slide 17, when we first binned this data, we constructed bins from 1.5 to under 2, 2 to under 2.5, 2.5 to under 3, etc. You'll see that between 1.5 and under 2, there's only one observation. So this first bin here, which is the bar representing the group from 1.5 to under 2, that goes to a height of 1. So the bars are representing the number of observations within each of the bins, not the values directly. Does that make sense? Okay, sweet. Any other questions? Okay. So the reason that, well, one of the main reasons that we want to visualize data, aside from the fact that it just makes it easier to absorb, is because we can also use these visualizations to describe what we call the distribution of the data set. Now, the distribution of the data set is going to be described using 2 main points. Those main points are what we call the modality and the shape of that distribution. Okay, here we go. It's on this side. All right, so when we construct a histogram in particular, and we can do the same thing with box plots, but technically histograms are the best, and we'll talk more about that later. When we construct a histogram, we're going to focus on describing it in 2 ways. So what we are describing when we talk about the shape of a histogram is the distribution of the data set. So the distribution of the data set simply means shape of the data, which even simpler we can just think of as shape of the histogram. Okay, now what does it mean to have shape? When we talk about shape, we're going to talk about 2 points: modality and skewness or symmetry. So modality is the easiest to define. It's basically just counting the number of modes or peaks that we can see in the data. Skewness and symmetry are contradicting descriptions. If something is skewed, it cannot be symmetric. If something is symmetric, it cannot be skewed. So if our data set is symmetric, that's the description. If our data set is not symmetric, it can either be skewed left or skewed to the right. Okay, so we're going to look at a few examples of this now. All right, so there are common shapes that we will see throughout the course. The most common shape would be what we refer to as, okay, so this is going to be the middle. The most common shape is what we would call unimodal symmetric. Okay. A unimodal symmetric shape is going to look something like this. Okay. So what we have here is one peak or mode. Okay, so this is an illustration where the shape has one peak or one mode, so unimodal, one mode. And the amount of information or the amount of area on each side of the middle or on each side of the peak is about the same. Okay, so same area on each side of peak. Okay, so symmetry basically just means that based off of the location of the mode, you have the same amount of area on each side. Now, there is a situation where this wouldn't necessarily be true, so it's better to say based off of the middle, you have the same amount of area on each side. I would say that it was bimodal. I would think of this as being bimodal, but we'll come back to it in a little bit. Okay, here we are. All right, so the last point that I just made was we're talking about area on each side of the middle. A lot of the time, or some of the time, the mode is going to fall right in the middle, like it does in the unimodal symmetric shape. So unimodal symmetric, that one individual mode gets situated right at the middle. But it's also possible that we observe shapes that look like this. Oh, sorry. Okay, so this is going to be the middle, and we have something that looks like this. Okay, so in this situation, you can see now that we are bimodal symmetric. So we have two modes. Right? But on each side of the middle, we still have the same amount of area. Okay. Yeah, unimodal symmetric is the most common. It's the shape that we're going to be seeing. It's the shape that we will work with and see the most often throughout this class. Okay, so with the bimodal symmetric illustration, you can see that we're talking about symmetry on each side of the middle now, which is the most general way of describing what we're trying to look for. So in this case, the peaks don't sit at the middle, but on each side of the middle, you have the same amount of information and you have peaks of the same height. So that would still be symmetry. All right. Now, the other shapes that we are going to be concerned with most often in this class are the two unimodal skewed shapes. Okay, so there's two different skews that we have to be familiar with. The first one is what we would call right or positive skew. So that's going to look something like this. So here we have again one mode. Okay. And this shape here so this shape here is what we would call unimodal right skewed. Now, it's worth pointing out that right skew and positive skew are the same. Okay, so an object that is right skewed is also positive skewed. That's an interchangeable definition. So when we're talking about skewness, we're talking about the direction of that skewed tail. So this part here, this is the skewed tail, okay? And it's moving to the right, or it's moving in positive direction. All right. Okay, so skewness is defined by the direction of the tail. Now, the other way that you can think about this, and personally, I think that this way is slightly more complicated because we're reversing direction, but with right skewed, the mode is to the left of the middle, sorry, to the left, right? So you can see in the illustration that our single mode here, this is to the left of the middle, which indicates skewness to the right. So that's another way that you can think about it. But what I prefer to do is just look at which direction the tail is heading. So the skewed tail is moving to the right side or to the positive side. So that's what makes it right skewed. Okay, so based off that definition, it would follow pretty naturally that our left skewed diagram is going to look very similar, except it'll just be the mirror image of the first one. So in this case, we might have something that looks like this. Right? So this would be unimodal left skewed. All right. And same idea as before. So we have one mode, and then we have skew tail going left. Skew tail to the left, right? And in this case, just like before, we can say left skew and negative skew are the same. Okay. So again, direction that the skewness is heading is how we define that the type of skewness. So we have unimodal right skewed when the tail goes right, and we have unimodal left skew when the tail goes left. And right and positive are the same thing. Left and negative are the same thing. Sorry, what's the last word that you just wrote down after moving in positive? Direction. Oh, you got it. Okay. Sorry about that. Try my best. Okay. So these are the common shapes that we're going to be dealing with throughout the class. The unimodal shapes more so than anything else, but there might be a couple of bimodal or trimodal objects that pop up from time to time. One of the questions that might come up is, how do you tell direction of skewness based off of a bimodal distribution? Typically, what I would do is base it off of the dominant mode. So whatever peak is the highest, base your direction of skewness off the highest peak. So if everything, even if there's multiple peaks, but they're to the right of the biggest one, that would be a right skew. If there's multiple peaks, but they're to the left of the biggest one, that would be a left skew. Okay, so base everything off of the highest peak, and then the same definitions that we just described would follow from that. Any questions about these shapes or these common shapes? Okay, so here are a couple of illustrations where we can take the shapes that we had just talked about and apply them to a histogram for a particular data set. So the idea here is essentially identify what would be considered kind of the midpoint based off of the axis you're working with. You can sketch a curve on top, and then you can use that curve to identify the shape. So for example, in histogram for data set 1, you can see that we range from -4 to +4. So the midpoint here is going to be right at 0. All right. And then if we were to sketch a curve, on top of this histogram, you can see that the curve's peak is right here. All right. The middle of the object is basically right at 0. All right. So we have effectively the same amount of area on each side of the peak. So this would be a unimodal symmetric histogram, or a unimodal symmetric shape. Sorry, the distribution of the data set would be unimodal symmetric. Okay. In the second illustration, we would do the same general thing. So we can see that the axis ranges from 0 to 40. So the midpoint would be right about here at 20. Right? And then if we were to try and sketch this shape, we would have something that looks like this. Right? So in this case, you can kind of see a peak here, though we're sort of running out of axis to work with, but that would be the general idea. So we'd sort of have like this kind of idea going on, if you will. All right, so again, what we can see is that there's one peak. In this case, we can see that the peak is left of the midpoint. So this would be a skew tail because it's definitely not symmetric. And this tail is moving right. So this would be unimodal right skewed. Okay. Okay, so let's go back to the histogram that's on slide 17 briefly and just talk about that shape because that's a little bit more difficult to diagnose. So slide 21, not slide 17. Okay, so in this illustration, what we would have here, I think, is something that looks like this. So we would have our first peak here, and then we're going to have a drop because there's no information, and then we're going to have something that goes down like this. Okay. So in this situation, we have two modes. And if we look at the axis, we can see that we're moving from roughly 1.5 to 5.5. So the midpoint is going to be right about here. All right. Now, this is a tricky one because of the height of the modes. But in this situation, the bulk of the area is to the right of the midpoint. Okay, so majority of area is right of midpoint. Okay, so most of it is on the other side. So therefore, I would be inclined to say that this is actually a bit of a left skew, because even though the first peak makes it difficult to see, you have less area to the left of the midpoint, which is typically what we would associate with a left skewness. Okay, so majority of area is right of the midpoint. Okay, so that means less area to left of midpoint. So slightly left skewed. Okay. So I think that it would be fair to classify this as being bimodal with a left skew, which again, I think is hard to see because that first mode masks it. But given that we have most of the area right of the midpoint and we have a smaller amount to the left, which is typically what we would associate with a left skew, that's why I've gone and classified it as being skewed to the left in this case. Any questions about that? How come the drop only comes down about halfway? How do we know if it doesn't? It's a rough approximation. That you can draw it as far down as you want for your purposes. It's just a bit of an approximation. No, not really. Like, so that part of it, you just want to make sure that what you are doing is recognizing that there's no data there. So those two modes would have to be separate from one another. They wouldn't be connected. Yeah, I guess you can do that, like multimodal. Typically for 3, you would do like trimodal. You could actually go trimodal, quad modal. I guess like quintuplet modal. But yeah, once we get beyond 3, we usually just use something like polymodal would work, or multimodal would be fine. Any other questions? Okay. All right, so what we have talked about so far today are binning approximations for quantitative data. And then we talked about histogram construction and describing the distribution of the data set. So again, when we say distribution of the data set, we're kind of just saying very, very informally shape of the histogram. That's essentially the idea. And the unimodal symmetric shape is the shape that you will want to familiarize yourself with, would be the shape that you would want to be most familiar with, because that is the shape we will see throughout the course. So that is a shape that will come back time and time again, and we will see that this particular shape inherits very good qualities and properties that we can utilize later on in this course. The next thing that we're going to talk about in this lecture set are actual numerical descriptive values. So up until this point, we haven't been focused on any kind of calculation. We've really just been focused on definitions, how to organize data based off of bins, and then how to sketch a graph based off of that binning procedure. When we talk about descriptive numerical statistics, we actually group the kinds that we are interested in into two different groups. So we're going to talk about locations of center or locations of the middle. And then we're going to talk about measures for describing what we call variation in the data. So these are going to be measures of spread. And these are things like the standard deviation and the percentiles. But we will look at a few other examples as well. So we're going to start off by talking about measures of center, which is somewhat of a misleading name, as you're going to see in a little bit, but we're going to group these three as measures of central tendency, more loosely defined. So these are values that we can utilize to find, in some cases, the midpoint of the data, though depending on the quantity we're talking about, we're going to see that that isn't really true, but we'll come back to that point in a little bit. The most common measure of center is the mean. And again, this is a misleading concept because the mean is actually only at the center if the data is symmetric. Otherwise, it's not located at the midpoint of the data. Nonetheless, the mean, which is a value that we will utilize throughout the course, is simply the sum of all of the values in the data set divided by the number of observations. So computing the mean is actually quite straightforward. In example 1, we have a very simple illustration of this idea. In this data set, we have the stopping distance of 13 cars that were traveling at various speeds. Okay, so here again, our variable is stopping distance, and this would appear to be discrete quantitative. All right, so we want to find the mean of these 13 stopping distances. To do that, we simply take the 13 values, we add them all together, and we divide by the number of values. So you can see here that we have literally that calculation being written out. So we're adding all the numbers in the data set together, dividing by 13, and that gives us 32.9 feet. So this would be the average stopping distance of the 13 cars. So we would say that on average, the 13 cars in our data set take 32.9 feet to come to a complete stop. You'll notice that I rounded to 1 decimal place beyond that used for the observations. So there might be a situation where you find in the assignment a notation or an instruction that indicates this, okay? So if you are asked to round to a decimal place beyond that used for the observations, this is what that means. Our data have 0 decimal places associated with them. So 1 decimal place beyond that used would just be 1 decimal place, which, so here 32.9 uses 1 decimal place more than the data. Therefore, that's 1 beyond what is used. Okay. Any questions? skip any? Okay, the next measure of center is the median. Now, the median is a particularly important measure of center because it actually lies at the middle of the data set. So this is, regardless of the shape, always going to be a representation of the true middle point of the data. The median doesn't require much in terms of calculation. It actually only requires that we order the data from smallest to largest value before we begin working with it. So for example, if we wanted to find the median of those 13 stopping distances that we discussed on the previous slide, that would be found by taking the 13 values that are shown on slide 30, arranging them from smallest to largest, and then identifying where the midpoint is. Okay, so here we have the ordered values. Okay, so we've ordered the data from smallest to largest from the previous slide. Now what we're going to do is identify which point falls in the middle. This is a relatively simple process. We simply count the number of points. So we have 1, 2, 3, 4, 5, 6, 7. Okay, I'll just write it. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 observations. The 7th observation is the middle point of the data because on each side of 7, you have 6 values. So here we have 6 values to the right. And here we have 6 to left of 32. Okay, so we have 6 values on each side of 32, which means that 32 is the midpoint because it falls in the middle of the data set. Right? So interpreting the median isn't quite as straightforward as interpreting the mean, but essentially what we can say is that this value represents the middle part of the data. So we can say something like in our data set of 13 stopping distances, 6 cars had stopping distances less than 32 and 6 cars had stopping distances greater than 32. Or something like the same number of cars had stopping distances greater than 32 and less than 32. That would work as well. We're just trying to describe that midpoint. Yes, the midpoint is always the median, or the median would be the midpoint of the data. Yeah. Okay. In the first illustration of the median, we were working with a data set that had an odd number of values. So 13 is an odd number. In general, whenever you have an odd number of values, the midpoint or the median will be an actual point in the data set. So it will be the observation that splits the data into 2 equal-sized halves. In the situation where we are working with a data set that has an even number of values. So for example, on slide 32, I have a data set that gives the ambient CO2 concentration of 10 different plants. Okay. And this, again, is quantitative discrete. The first thing we do is we start by organizing the data from smallest to largest. Okay, so this is the original data. And then this is the ordered data. Now, in this situation, we have 10 observations, which means that there are 2 values that fall in the middle. Okay, so this is the 4th observation, or sorry, this is the 5th observation, and the 6th observation. So there isn't an actual number in the data set that splits the data into 2 equal halves. The midpoint is actually here. Okay, so the middle for an even number data set is going to be a value that falls between the 2 center points. So that means that the midpoint or the median here is going to be the average of 250 and 250. Okay. So in this case, the median is going to be 250 plus 250 over 2, which is equal to 250. So for an even number data set, you take the 2 midpoints and add them together and divide by 2. So you're finding the average of those 2 middle points in order to find the median. And then you can see that this midpoint splits the data into 2 equal size halves, which are halves of size 5. Okay. So for odd number data sets, the median is a point or an observation in the data. For even number data sets, the midpoint is the average of the 2 middle values. Okay. Any questions? The last measure of central tendency that we're going to talk about today is the mode. The mode is actually not a value that we need to calculate at all. The mode is simply the number or the numbers that occur most often in a data set. So for example, for the 13 stopping distances of the cars, we have 2 modes, the values 32 and 34. Because those numbers occur more than any other number in the data set. For the CO2 concentration example that we had just looked at, our mode is equal to 250 because this is the number in the data set that occurs more often than any other mode. Sorry, that occurs more often than any other value. So the mode is simply the value that occurs most often. And actually, the interesting part is that the mode really isn't a measure of center at all. Sometimes it'll be located at the center. In the case of symmetric data sets, this would most likely be the case. But it's simply just the value that appears most often. In some situations, there might not even be a mode. So if we're working with continuous quantitative data where every value is unique, we wouldn't have a mode in that case because every single value only occurs once. So in situations where we have repetition, we can find a mode, and there doesn't have to be just one, there can be multiple, as for example, in the first case shown here. Any questions about that? Okay, so let's use the last 5 minutes here to work through an illustration of all 3 of these measures of center at the same time. Okay, our data set here actually has 2 variables associated with it. So our first variable is the month. And our second variable is the number of airline passengers. Okay, so we have 2 variables in this data set. The month of the year, and then the number of airline passengers would be the second variable, right? So in this case, variable 1 is qualitative, and variable 2 is quantitative discrete. Okay, so we're gonna start we're gonna find the mean, the median, and the mode for the variables in this data set. The first thing that we can recognize is that for a qualitative variable, there is no mean or median. So the mean and the median are unique to quantitative data, but the mode can be found for both qualitative data and quantitative data. All right. So let's start by ordering the data set, because this is going to be useful for this will be a useful practice for us both in terms of finding the mode and finding the median. Adina, so never a mean or median for qualitative data. Yeah, that's correct. So you can't find a mean or a median for qualitative data. So let's start by ordering. So step 1, order data. Okay, so this is going to give us 390, 391, 417, 419, 432, 461, 461, 472, 508, 535, 606, 622. All right. Okay, now let's do the median. It doesn't matter what order you do these calculations in, but well, I'll just start with the median. Okay, so we have 12 observations. So the median, so this falls between 461 and 461. So we can see that the median is going to be in between the two 461s, because on each side of that, we will have 6 values. Okay. Therefore, the median equals 461 plus 461 over 2, which is 461. Any questions about that? All right, so if there's no questions, I'll just stop there. I thought I would have enough time, but it's 9:20 now. So we'll stop here for today. And on Tuesday, we will pick up with this example, and then we will continue to talk about measures of spread. And then we'll talk about box plot construction, and we'll see how far we can get on Tuesday. So have a good weekend. I'll post the video as usual. Please take a look at assignment 1. And yeah, I'll talk to you guys on Tuesday.